Okay, so today we will study the completeness of the Hilbert system for first order logic, right. Maybe what one should briefly look at is are these rules. So, as far as the Hilbert system is concerned, okay, first thing of course, for propositional logic we had this interesting concept of being able to simulate the truth table, right. So we actually simulated truth tables. We showed that every row of the truth table can be simulated by a proof in the propositional Hilbert system, and then after that it was that was the hardest part, simulating each row, and having simulated each row, then we could just prove that every tautology is a formal theorem of H naught. In the context of first order logic, we have to make certain things clear. I mean, so in the context of first order logic, there are free variables. That is one extra complication, and terms, and essentially Hilbert terms. And if there is at least one constant and at least one function symbol, then the number of Hilbert terms, ground terms, is infinite automatically, right. So, as a result, so which means that truth tables are not possible. I mean, so this whole concept of trying to simulate truth tables should go. The second thing is that, so what we essentially showed in the propositional Hilbert style system is that you can prove every tautology as a formal theorem, and your and the soundness essentially showed that anything that is provable is a tautology, right. So that is how the soundness and completeness went, and the deduction theorem allowed you to move formulae to the left of the turnstile, and therefore give you a complete system for logical consequence also. So it was sufficient to just look at tautologies and whether every tautology is provable, and for soundness it was sufficient to say whether anything that is provable is indeed a tautology, right. Anything that is provable from no assumptions, basically. I mean, that's, if that is a tautology, then you are essentially done, right. So here of course, and the technique involved using trying to simulate truth tables, but of course with in the first order logic, because of the presence of free variables and the ground terms of the Hilbert universe, truth tables are never finite anyway. So therefore there is no question of any kind of finite proof simulating each row of the truth table and trying to take a conjunction of all those rows. I mean, it makes absolutely no sense. Yeah. On the other hand, so this technique that was used for propositional logic is clearly not suitable for first order logic, even with just a single constant in the signature and even with a single operator function. Yeah. The other thing that is interesting is this notion of a tautology. I mean, this is something I did not probably clarify before. The difference between validity and tautology. So what we will do is, I will take the view, okay, let me call this versus tautology, right. So we have used two different terms, but then in first order logic the two terms are actually different. So so they are different in a certain sense, and that sense is that we would think of, let us say, a predicate phi which might have various free variables. Okay. We defined this as its validity, and basically we said that it is valid if for all models, for all sigma models, it is indeed true. Okay. So there are there are formulas like for all x p of x and q of x implies for all x p of x and for all x q of x. So, if you were to take a formula like this, right, this formula is clearly valid. Okay. So, this is a valid formula, but it is not a tautology. Okay. It is not a tautology because the notion of a tautology essentially comes from propositional logic. And loosely speaking, what I had said before about a tautology was that it should have one of those tautological forms. So, for example, this, so even if it has free variables, I do not care, but take this. If you take this, this has a tautological form, let us say, yeah. Or let's stick. Oh, okay. Since I am using anyway the entire language, it does not matter. So, this is also valid for all models. It is true that with a unary relation P in it, this is always going to be true. Okay. So, this is valid because it is a tautological form. I mean, it has the same shape. The tree looks like a typical propositional tautology, with the difference that instead of the leaf being a propositional atom, it is actually a predicate with free variables. But then the free variables match. So, for example, this is not a tautology, right. Say Px or not Py. I mean, this is not a tautology. It is not in a tautological form, and it is therefore also not a tautology. And it is clear that this is not valid, because I can always find a model in which by giving x and y certain different values and by interpreting P in a certain way, I can make this false, for example. Yeah. So, this is not a tautology, whereas this is a tautology and it is also valid. This formula is not a tautological form, but it is valid, right. So, in general, if you want a so this notion of a tautological form is something that I did not actually formalize, but now in the light of the Hilbert style proof system, we can actually formalize it. So, we will just say a tautology in first order logic is any formula that can be proved using only the axioms k, s, n and modus ponens. That means, you do not use any of the quantifier rules of any of the quantifier axioms. Okay. So, even if the formula is open in the sense that it has free variables, if the proof, so all these things like, so therefore, Px arrow Px, we have already seen a proof of this, right, in propositions. So, a proof of this will involve entirely just H naught, I mean that is just the axioms and proof rules of the propositional fragment of the Hilbert set proof system, right. Whereas, the validity of this formula cannot be proven in just H naught, because of the fact that you are distributing quantifiers. You have to, so you will have to use a you will have to first eliminate the universal quantifier by an instantiation, and then you will have to generalize the resulting formulae again by universal quantifier introduction. So, you will be using some of the proof rules of H1 which are not there in H naught, and so even though this is valid, this is not a tautology, right. Okay. So, the corresponding analog for first order logic is really just that we want to show that every valid formula can be proven. The soundness theorem that we proved already showed that any formula that you can prove is actually valid, right. I mean, that is one of the things that we, where did we show that? So, did we somewhere here, I think somewhere, oh, this was resolution soundness, and did we prove the soundness of the Hilbert's alpha conversion deduction theorem? Every theorem of H1 is logically valid. So, we have shown that. Now, what we need to show is the converse, that every theorem that you can prove in H1 is actually every valid formula can be proven, basically, right. Okay. So, for that what we will use is, so now that automatically brings in the fact that there might be infinitary sets and so on and so forth. So, what we will take now is, so there was, we had in our propositional logic, we had this notion of maximal consistent sets, and if you remember the notion of maximal consistent sets, we actually did, here it is. If you remember this was all done model theoretically, okay, in the sense that we used the notion of consistency based on truth, based on truth assignment. So, we were basically looking at models. I mean, I remember, I mean, my color coding is such that, you know, anything that was brown in color was a model, and anything that was green and or black and so on and so forth was proof theoretic, right. I mean, so in the case of maximal consistent sets and so on, we actually used the semantics, therefore, we used models basically, and we defined notions of properties of finite character, and we showed that you can extend a set, a consistent set, to a maximal consistent set. We showed there are many that Hintika sets are in some sense maximally consistent, or any maximally consistent set is also a Hintika set, and so on, and then we had Lindenbaum's theorem and so on. All this was done with by referring to the notion of truth, and therefore, the model, the underlying truth valuation model that you had for propositional logic, and it was possible to do these things in propositional logic because our truth valuation model was just a 2-element truth valuation model, and therefore, anything that was if you started off with something finite, you continue to remain finite always. Now, that luxury is again not available directly in first order logic. So, the only finiteness that you have in first order logic is the notion of proof. So, the exact analog of these terms can also be defined proof theoretically in terms of, so what I am saying is, this is the analogy. So, the notion of a tautology was defined model theoretically through the notion of truth. The notion of validity was also defined through the notion of truth, and so on and so forth. But the notion of a tautology in first order logic can be defined proof theoretically by just saying that if there is a proof that uses only the propositional axioms and rules of inference, then it is a tautology, and in fact that is a fairly sound way. So, there you have, if you have soundness and completeness, then you have proof theoretic analogues also for model theoretic concepts. So, the notions of validity and the notions of tautologousness and so on, the notion of maximal consistent set, the notion of compactness, that is another thing. So, we defined compactness entirely through the Tableau proof system, and we actually used this notion of unsatisfiability and so on and so forth. We used a lot of model theoretic concepts there, but it is possible to also transform that notion of compactness to what is known as deductive compactness. Okay. So, what are we saying now by deductive compactness? I am saying that a certain formula phi is a logical consequence or is I mean I am sorry, given a set of formulae capital phi, yeah, this is unsatisfiable if and only if it is possible to prove a contradiction such as not of phi arrow phi for some formula phi. Okay. It is consistent if and only if you cannot prove any contradiction. Okay. So, notice the use of these symbols are all very important, right. I mean this is a model theoretic symbol, right, logical validity, but provability is a proof theoretic symbol. Yeah. So, you have to distinguish between the two. Yeah. So, what we will do now as a technique for proving, so Gödel's technique for proving completeness of the Hilbert style proof system is essentially that of transforming all those model theoretic concepts into corresponding proof theoretic concepts. Okay. And so that's what actually happens here. So we'll so with that introduction, let me start this. So firstly, the notion of consistent sets was defined. Tell that guy to go and sleep in his hostel. Yeah. Why do you want to come and sleep here? Sleep in the hostel, it is quite cool now. Okay. So, the notion of consistency was defined in terms of whether it was possible to find a model for it, whether it was possible to give a truth assignment which will make all the formulas in a set true. Okay. Now, we will talk about deductive consistency, and so by the way, this is my term. I want to clearly separate out model theoretic concepts and the corresponding proof theoretic concepts. So, you may not find this term expressed as deductive consistency. It might, depending upon the view of the author, whether he is taking a proof theoretic view or a model theoretic view, he might just call it consistency, right. So, given a set phi, and of course, we are restricting ourselves to the language consisting of just the universal quantifier, not and arrow, right, that is L1 of sigma. So, this set phi is deductively consistent. So, I am making it completely pure, deduction is proof, right, I mean you deduce something, you give a proof. So, it is deductively consistent as opposed to just being consistent in a model theoretic fashion, is deductively consistent if and only if there does not exist a formula such that both formula phi such that both phi and its negation can be proven from the Hilbert style system. Notice again that this is completely proof theoretic. So, we are not looking at interpretations, we are not looking at models, nothing. Now, we are looking at consistency just from the point of view of the consistency of a formal theory, if you like, right. So, if you cannot prove both a formula and its negation from the given set of formulae phi, then you somehow say that this set phi is consistent. And in fact, a consistent formal theory will be one in which not all formulae are theorems, right, and that follows from this fact. You remember this axiom, the bottom axiom, and then if you use the deduction theorem, essentially if you can prove for some formula phi, if you can prove both not phi and phi, then you can conclude any formula psi, right. Okay. So, which means an inconsistent theory is one in which every formula is provable. Okay. And And model theoretically, what does that work out to? It works out to just saying that a set phi is inconsistent if and only if every formula is a logical consequence of that set, okay, which it will always be, because if phi itself, the conjunction of all formulae in phi is always false, then that is anyway imply any other formula, and therefore all formulas will be implied by that, right. So the two notions go in sort of parallel, yeah. So, however, so this is a perfectly valid notion of consistency, okay, and it just says that you should not be able to prove a contradiction anywhere using just. So, if you think of your phi as the set of axioms of a formal theory, then you should not be able to ever prove a contradiction, yeah. So, they should, okay. So, the other possible so here are equivalent statements. So, you should not be able to prove both the formula and its negation as valid proof theoretic consequences of your set phi. You should not be able to prove a single contradiction like not of psi or psi for any psi, or simple, you should not be able to prove every formula. There should be at least one formula which you cannot prove, then your set phi is consistent, yeah. So, all these are equivalent definitions of consistency, and any or all of them may be found in books in various forms, but let's live with this. Let's live with this. Actually, we can live with all three, all these three definitions, and they are all equally valid, yeah. And sometimes we can, it is convenient to use one rather than the other, okay. Now, going back to the model theory. So, what are we saying? We have to have this plain assurance that if a set of formulas has a model, then it must be deductively consistent. If it is not deductively consistent, there is something seriously wrong with our entire framework of logic, and that is why this lemma is important. It is important from the overall point of view of the whole of logic. I mean, this is how for the last 2000 years we have been looking at mathematical theories, yeah. So this lemma has a very trivial proof, however, and that is that supposing you take this set phi which has a model A, that means in A, notice the brown color, every formula in phi is true in A. If phi is not deductively consistent, then there exists some formula phi such that both phi and its negation are provable in the Hilbert system, yeah. But the Hilbert system is sound, that is something we have seen, which means that if it is sound, then it follows that whatever you prove is also valid. So, this model should satisfy both phi and its negation, and that is not possible, and so therefore, our notion of deductive consistency is fine, okay. Right. Then just like we did maximal consistent sets, I will talk about deductively complete sets, okay. So, this it's really like a notion of maximal consistency. What was our notion of maximal consistency? That for any formula phi, capital phi is maximally consistent if for every formula small phi, either phi or not phi is in the set, right. And this is, however, this deductive completeness for us comes at a certain price, and that is that we cannot, with the presence of free variables, we cannot just take phi and not phi. We have to take its universal closure, okay. So, completeness, and from this notion of deductive completeness, the completeness of the Hilbert style system will follow, and that is only for essentially for universally quantified formulae, yeah, for closed formulae. So, for any set phi of formulae, firstly we know that even if phi has free variables, phi can be proven from capital Phi if and only if its universal closure can be proven from capital Phi, right. Otherwise, what happens is you have all those problems about free variables and admissibility of substitutions and so on and so forth, right. So, if you can prove phi without worrying about all that, then it does not, then it means what you are essentially saying is you do not care how the free variables are substituted, it is still going to be true, which is equivalent to saying that if I universally quantified, it will always be true. Yeah. So, for any set capital Phi, small phi is provable from capital Phi if and only if the universal closure of small phi is provable from capital Phi, if and only if phi union not of the universal closure of phi is not deductively consistent. This is, yeah. So, just take this. So, this portion is something that I have repeated several times before, but this one, this notion of we always went between logical consequence and unsatisfiability, right, or inconsistency, right. We took the negation on the right hand side and pushed it into the to find a give a set of formula, and we said that that is unsatisfiable or inconsistent. But now what we are saying is that just taking this negation of phi itself and putting it into adding it to capital Phi may not make this deductively inconsistent, but you take the universal closure of phi, negate it and then put it in, then you have some chance of getting something that is unsatisfiable, right. Okay, so let us just look at the proof of this lemma. Okay, one thing is, so this the fact that this first part small phi is provable from capital Phi if and only if its universal closure is provable from capital Phi follows from these rules, right, for all elimination and for all introduction, yeah, it follows from them, and I will leave it as obvious, yeah. Okay. So, which means okay, let's go here, yeah. Okay, so now supposing, now what we have to show is that if phi is what we are going to show is that if phi union negation of the universal closure of phi is not deductively consistent if and only if phi is provable from capital Phi. That is what you are going to prove, yeah. So, let us assume that you can prove phi from capital Phi. Then one thing is, by monotonicity, by adding extra assumptions, you do not destroy that proof. Even if you added contradictory assumptions, it does not matter, that is, yeah. So, let us add this not of for all phi, and I can still prove phi from the same proof holds, basically just yeah, by monotonicity. So, what this, so now from this first part it follows that if I can prove phi from this set of assumptions, then I can also prove the universal closure of phi from this set of assumptions, okay. In other words, and further, any assumption itself is provable from this set of assumptions. So, I have proven both the universal closure of phi and the negation of the universal closure of phi, and therefore, it follows that this set phi union the negation of the universal closure is not deductively consistent, right. Okay. The other way, suppose phi union not of the universal closure is not deductively consistent. If it is not deductively consistent, then there exists some formula which there exists some formula phi such that phi and its negation can be proven, right. So, there exists some formula psi such that phi union this proves not of psi arrow psi. So, I am essentially using this characterization. Yeah. Okay. If so, I can prove not of psi arrow psi from these assumptions, and then I can use this psi arrow psi is a theorem of both H naught and H 1. It does not matter what it is, it is a tautology, right. So, it always holds, and then we have this bottom rule somewhere, right. If you can prove a formula and its negation, then you can basically infer anything you like, right. So, by using this we obtain that I can prove the universal closure of phi. Okay. Then if you remember, when we did the deduction theorem, we said that if phi is a closed formula, then I can actually move phi on either side of the turnstile, yeah, appropriately. So, I can use this corollary to show that, and since we are dealing with only closed formulae, there are no free variables. So, all those side conditions are not applicable. The side conditions for all elimination and for all introduction are not applicable. The deduction theorem is also applicable, since we are dealing with only closed formulae. So, which means from phi I can prove not of the universal closure of phi arrow universal closure of phi. Okay. So, then it is also possible to show, by this I should have probably made this an exercise, but I did not. It is possible to show that actually since it is possible to show that if I can get not phi arrow okay, let us say not psi arrow psi arrow psi, I mean that is a theorem that you can easily show using one of these derived rules that we have done. So, if you can prove that, then by a single application of modus ponens we have proved that the universal closure of phi can be proven from phi. Okay. Right. So, the importance of that universal closure in first order logic as opposed to whatever we did in propositional logic is absolutely required. I mean that without, supposing you did not have that universal closure, then the general inconsistency you add not phi, it will not imply that. If phi arrow not phi is inconsistent, then that does not imply that you can prove phi from phi, because you take this set capital phi to be not of for all x not p of x, and take small phi to be p of x. Okay. Then phi union not of p of x is inconsistent, because for whenever this formula is true, this can under no valuation can this not p of x be, yeah. So, phi union not p of x is inconsistent, but it is not possible to prove that p of x follows from not of for all x not p of x. Is that clear? I mean, there is a lot of negation going on, but you guys are so this is essentially equivalent to saying that there exists an x such that p of x is true, okay, and saying there exists an x such that p of x is true and not p of x, that is inconsistent, because I can find some model which under any valuation that will be actually inconsistent. However, I cannot move this thing around because of this free variable, precisely for the constraints that were there in the deduction theorem. For the same kinds of reasons of the use of free variables and so on, I cannot prove this, that p of x follows from phi, because anyway this is inconsistent, right. Okay. So, what happens therefore is that what were the notion of maximally consistent sets in propositional logic translates into deductively complete sets in first order logic. But deductively complete sets are require universal closure, and when you do universal closure there are no free variables, and that is essentially like having a proposition, they are all propositions. So, they directly translate into essentially closed sets of closed formulae, and that is what, and this is the maximal. So essentially what we are doing therefore is we are restricting ourselves to basically just closed formulae. What can be proven using closed formulae? And our notion of completeness is also going to be restricted to that, which is not a severe restriction, because in any mathematical theory, what are you trying to do? When you prove a theorem, you are trying to prove essentially closed formulae. Okay? If there are, so you are essentially trying to prove closed formulae, and if there are particular cases to be considered, then you are essentially proving closed formulae of the form there exists something which satisfies some property. Otherwise, you are trying to prove essentially universal formulae. In either case, you are essentially trying to prove closed formulae. So, from the point of view of the consistency of a theory and the completeness of a theory, this is not a serious restriction. Yeah, and so which brings us actually to Gödel's completeness theorem. This just says that if phi is a logical consequence of capital phi, then phi is provable from capital phi. Okay, which is equivalent to now of course, since we cannot move things, since the deduction since phi might have some free variables and so on, you cannot keep moving it on either side of the turnstile because of the restrictions posed by the deduction theorem, the notion of use of free variables and so on and so forth. However, when this set phi is empty, what you are essentially saying is that every valid formula would be provable in H1, which is what we want. The corresponding notion from tautologies is that of valid formulae, and what you are essentially saying is that every valid formula can be proven in the Hilbert Strat system. So, and actually after all that preparation, this proof is actually quite trivial. So you assume that it is a proof by contradiction, assume that small phi is a logical consequence of capital phi. Notice that capital phi can be an infinite set. I mean, we are not putting any restrictions of finiteness. However, for any proof, you will be using only a finite number of assumptions, because a proof has to be a finite tree, and if it is a finite tree, then you are using only a finite number of the assumptions as leaf nodes. Yeah. So, supposing phi is not provable from capital phi under H1, then what it means is phi union the negation of the universal closure of phi is deductively consistent and hence possesses a model A. But that implies that every formula in capital phi is true in this model A, but this formula phi itself is not true in model A, which by definition means that this phi, that means A is a model which shows that even though every formula in capital phi is true, the small phi is not true. So, it shows that small phi is not a logical consequence of capital phi, right. Okay. So, and that is a contradiction, and therefore, it follows that this assumption that phi is not provable from capital phi is okay. So, this once you have done this, once you have translated all your notions from propositional logic and from model theory into first order logic, the proof of this theorem becomes quite simple, right. So, now what you should look at actually is, so what does this completeness mean? This completeness just means we have proven that there is a structure to mathematical theories. Okay. So, supposing you take the theory of partial orders, for example, then what you are saying is, or supposing you have created a new mathematical theory with some axioms, yeah, then what you are saying is, let us look at the first order theory of that structure, of that system of axioms. Then you have a hierarchy of using reasoning from first order logic, on top of which you have you will also add your axioms of your theory, right. So, let us so if it is group theory, then you are going to add the group axioms. If it is a theory of monoids, then you are going to add the monoid axioms. If it is Euclidean geometry, then you are going to add the Euclidean geometry axioms, but those Euclidean geometry axioms will reside on top of the axioms for real numbers. There is a modular, what I am trying to say is that there is a modular structure in mathematics such that you actually build one on top of the other. So, you take any theorem, supposing there is some valid formula here expressed, supposing there is some valid form. If this formula in this theory is valid, but supposing you are not able to prove it, supposing it is not provable with these axioms. So, what are you saying? You are going to take this is your Hilbert style axiom system, you are going to take the set of axioms and now you are going to essentially try to prove theorems. So, you try to prove using H1 union A, you essentially try to prove this phi and you find that it is not provable. Okay. Then what does it mean? It means that your axioms are not sufficient. The fact that you cannot prove a logical consequence which holds in that theory in first order logic is not due to the insufficiency of the logical axioms, but it is due to the insufficiency of the axioms you have used for that theory. That is what this completeness says. What this completeness says is, if I am going to, I cannot put the blame for incompleteness in a mathematical theory, or in a first order mathematical theory, on anything to do with just the axioms of first order logic. I have to put the blame for that incompleteness roundly on my axiom system. So, I have to look now for maybe extra axioms to complete it. So, you understand. So, that is what this completeness means. Remember that we are showing this completeness independent of any particular theory. We have taken, it is just parameterized on sigma, that is it, right. So, what does it mean? That your theories also have a certain modular structure in your mathematics, and it is necessary to be convinced. And so the importance of this theorem lies in the fact that what Gödel essentially has said is that if you are finding that there is some logically valid formula that you cannot prove in your theory, do not put the blame on first order logic, put the blame on your axiom system. You probably do not have enough axioms, or you do not have sufficiently powerful axioms which will capture all the logical consequences that you want. Okay. So, it is interesting that, so that is what this completeness says, right, that as far as first order theories themselves are concerned, the Hilbert style system is complete. For particular theories, the incompleteness comes from the axioms of that theory and not from first order logic. But what does happen in the larger picture is that if I look at the first order theory of topologies or neighborhood systems or whatever, then very often properties that I am expressing are not first order expressible. Okay. I may not be able to express it as a finite formula in first order logic. That problem exists, in which case I may not be able to prove. Then I do not know whether I am not able to prove because I do not have sufficiently powerful axioms, or because I am not able to express my properties in first order logic. Okay. So, the larger structure of mathematics or mathematical reasoning is that it does follow this hierarchy of a reasoning system. So, what we are saying is that your basic reasoning system is basic first order reasoning system is complete and valid. All the incompleteness that comes is either because of inexpressiveness or because the axiom system for the theory that you are building on top of this is not powerful enough. Yeah. So, this was the first step that Gödel had to take before he could prove that first order number theory is incomplete. That's first order number theory is incomplete, then it was natural for Gödel to look for the reasons in first order number theory itself. Once he had proved this theorem, he did not have to look at reasoning systems within first order logic, he had to look for it in number theory. That is a clear stratification, that stratification is absolutely important, otherwise nobody had that idea, including Hilbert, that there is a stratified way of looking at theories. Even though Hilbert had given a complete axiom system for Euclidean geometry, he did not fully realize that he had already a complete first order reasoning system. On top of that, he may not have had a complete theory of the reals, but he had enough axioms, in fact just the field axioms of the reals, which basically dealt with addition multiplication. What do you require for Euclidean geometry? You do not require more than addition and multiplication. The field axioms and the properties for reals using just addition and multiplication were enough, and you could build Euclidean geometry on top of that and prove that your axiom system for Euclidean geometry was complete. He did not use any, because really you require addition because you want to add angles, you want to look at interiors, you want to look at line segments, divide them up, look at betweenness, and well, in the case of the similarities you are looking at ratios, in the case of the Pythagorean theorem you are looking at squares, but both of them correspond to essentially multiplication. So, as long as I had all the axioms related to addition and multiplication, I was doing fine. I just had to take care of ratios which, for example, the denominator should not be a 0, right. So, in every theorem where there was a problem of similarity, you have to make sure that, for example, if one side of a triangle is got 0 length, then you do not actually have a triangle and you have to make that clear, right. If one angle of a triangle is 0, then you do not actually have a triangle, you have to make all that clear. So, all those things that the angles have to be greater than 0 and this line segments have to have lengths greater than 0, you just put in all those conditions and then to ensure that you get proper triangles. And of course, in the case of triangles, you should ensure that your interior angles do not exceed or always less than 180, you should put that also, otherwise you do not have really a triangle. And once you add all those conditions rigorously, you can and with the theory of reals need not be complete. It is just that the field axioms for reals should be there, because those are the only operations you are using. Your first order theory of Euclidean geometry is going to use only those, addition, multiplication, that is it. Squaring is just multiplication. Ratios are also essentially expressed as there exists something such that when you multiply something you get something, right. And so all those things are expressible, and he could prove. So, Hilbert could prove the completeness of Euclidean geometry, but he did not realize that there is a stratified way of looking at it, which Gödel realized. So, if you just look at the first order theory of numbers as just being built on top of first order logic, then Gödel got his incompleteness, which basically showed that just the finite set of axioms that you put on numbers is not sufficient to guarantee all that you can prove all valid properties. Yeah. I will not go into Gödel's incompleteness theorem, which is that because that will take us too far away and we do not have enough time for that. But what I will do from next time onwards is I will just look at some very simple basic first order theories, and basically we will use this kind of stratification. Yeah. So, we will assume that our first order logic is complete, and we will just add this set of axioms, and we just say okay, whatever can be proven from this is the first order theory of that structure. Yeah. So, I will stop here at this point.